So let's look at an example here. A system moves from state A to state B, during which time it gains 400 joules of heat and does 100 joules of work, right? So that's a work by the gas, right? So it's a negative work on. What is the change in internal energy of the system? And so we can say the change in E internal, maybe we write it this way, is equal to Q in, going from A to B, minus the work by, going from A to B. And so that means the change in E internal, going from A to B, is equal to 400 joules minus 100 joules, or 300 joules. Just for completeness, I'll just write this equation the other way. So instead of saying minus the work by, I can say plus the work on. So it's 400 joules. That's the heat in. But since the work is being done by the gas, the work done on the gas is negative when the gas is doing the work. And so it's plus work on, but that's still minus 100 joules. It would be, if I wanted to be really specific, I would say this was plus negative 100 joules, which is still 300 joules. Right. So if you want, you can draw this actually on a PV diagram, right? I could just say, here's my pressure and here's my volume, and here is state A, right? And this is P, V, and say temperature, right? And here's state B. This is A, and this is state B, and this is P, V, T, right? And so when a gas is in a specific state, it's got a specific internal energy that's determined by that state. If it's a monatomic gas, the internal energy is just 3/2 nkt, right? And so once the state is specified, its internal energy is specified. And so going from here to here, I can just look at these two internal energies and know that they're going to be 300 joules apart. It's going from A to B, it's going to have to gain 300 joules of energy to do that. And it doesn't matter how it gets there. So it could, going from there to there, obviously in order to get from this state to this state, the pressure has to change, the volume has to change, and the temperature has to change. But it can go this way, or this way, or this way, or this way, and so on. When it ends up here, if it starts here, the change in internal energy is 300 joules. Furthermore, if it goes back the other way, change in E internal going from B to A is minus 300 joules. And we know that because if it ends up back at A, its total change in energy has to be 0. And so it goes from A to B and back to A, right? The change in internal energy going from A to A has to be equal to 0, but what is that? That's the change in internal energy going from A to B plus the change in internal energy going from B to A. And that means these two are the negative of each other. By the way, this does not say that QAB equals minus QBA, because the work and the heat can depend on the path. It's just that when you add them up, it has to be a constant. And I'll give you some examples of how that works. So in this problem it says, consider a gas going between states A and C via either ABC or ADC. Obviously it can go on any thermodynamic path from A to C, but we're going to look at ABC versus ADC. We're saying, look, when it goes on ABC, the heat added, they're telling us, is 515 joules. Furthermore, it tells us, these are horizontal lines and vertical lines, that P1, the pressure initially at A, is 2.1 times 10 to the 5th pascals. P2, the pressure at C, is 1.05 times 10 to the 5th pascals. V1, the volume at the initial position, is 2.25 times 10 to the minus 3 cubic meters. Similarly, V2 is twice that. And the question is, what is Qn ADC? So we know, since they start and end at the same point, that the change in internal energy along ABC is equal to the change in internal energy along ADC, because they end up at the same, start and end at the same points. And so it's the internal energy here minus the internal energy here, and what their internal energy is does not depend on the path they took. And so we can first evaluate this number. We can say, look, the change in internal energy along ABC is equal to Qn along ABC plus the work on along ABC. And there are a couple things to notice. First of all, the work on a gas is equal to minus the work by the gas, right? And the work by the gas is equal to the pressure, the integral of the pressure d volume going from one point to another point. When the volume is increasing, a gas is doing work. So we could also say, work on is equal to minus the integral from A to C of P dV. Right? When volume is increasing, positive work is being done. If something is expanding, the gas inside is doing work, pushing outward over a distance. The only way for work to be done on a gas is if the volume is decreasing, and so work on would be positive, including its negative sign, if the volume at C were smaller than the volume at A. And so I'd have a negative number in the integral and another negative sign to make it positive. So get comfortable with those ideas, and we're just going to evaluate, for now, we're just going to go ahead and evaluate the work by the gas going ABC, right? And so this is the integral, it's this integral, right? And so, but we're going to break it into two integrals. We're going to say it's the integral from A to B of P dV plus the integral from B to C of P dV. And I'm just going to say right away that going from B to C, there's no change in volume. This is an isometric path, and so, or isochoric, depending on which word you want to use. And there's no change in volume, and so no work is done along that path. The work is done along this path. And if you notice, the work along this path is at constant volume, and so it's equal to P1 times the integral from A to B of d volume, right? But that's just the integral of dv is just v, and so it's equal to P1 times the evaluation from A to B of of v, which is just P1 times V2 minus V1, because the volume at B is V2 and the volume at A is V1. And so the work by the gas along the path ABC is equal to P1, which is 2.1 times 10 to the 5th pascals, times that one minus that one, right? That one minus that one is V2 minus V1, which is 4.5 times 10 to the minus 3 meters cubed minus 2.25 times 10 to the minus 3 meters cubed. And what I get for that is about 473 joules. That's the work by, right? And so I'm going to erase myself back up to here and reevaluate this internal energy. I know this QNABC is 515 joules, and I know the work on is minus the work by, and so the work on is minus 473 joules. And so if I just erase a little bit of this, keeping maybe my numbers at the bottom, right, I'm going to get change in internal energy along ABC is 515 joules minus 473 joules, which is, I'm going to say, 42 joules. So that's the change in internal energy going on that route, right? And now I'm going to say the change in internal energy along ADC has to be the same thing. And what that is Q in along ADC plus the work on going from ADC, right? And so once again, there's no work. This is just so work on going from A to D to C is minus the work by and the work by going from A to D to C is the integral of P dV from A to D, sorry, so the work done going from here to here plus the work done going from here to here. This guy is 0 because there's no change in volume, and so work by ADC is equal to, once again I've got a constant pressure, and so it's just P2 times the integral from D to C of dV, and that's equal to P2, which is 1.05 times 10 to the 5th pascals. Erase just a little of that, times D to C. Well, I'll just evaluate that, right? It's just the volume. It's just V2 minus V1, which is 4.5 times 10 to the minus 3 meters cubed minus 2.25 times 10 to the minus 3 meters cubed. And that gives me about 236 joules. So this is the work by on the ADC path. And so if I come up here, I get, this is Q in ADC. There's work done by the gas, and so that means negative work done on the gas. It's minus 236 joules here. And so now I have 42 joules equals Qn ADC minus 236 joules, or Qn ADC is equal to 236 joules plus 42 joules, which is 278 joules. And so if I go this route, I have 515 joules of heat added minus 473 joules of work done. Here I have 278 joules of heat added minus 236 joules of work done. In both cases, heat is added, but work is done by the gas on the way, so a lot of the heat that's added just got converted to work done. And in both cases, I end up with 42 joules as the overall change in internal energy from going from A to C, following either path. The answer to the question, what is Qn ADC, is 278 joules. So in this problem, we're going to look at heat being added to one mole of an ideal monatomic gas. And so a monatomic gas means 3 degrees of freedom. That's what it really means. Heat is added to a monatomic gas isothermally, in other words, at constant temperature. And so until the final volume is equal to the initial volume times 3. And so you can think of here as our standard sort of piston problem, right? And so normally, your gas is in here, right? Normally, if a gas expands, it's doing work and it loses internal energy and cools. But what we're saying here is we're adding just enough heat under here so that as the gas expands and does work, it gains an amount of heat to keep it from cooling. And so we can say, what's the change in internal energy for this process? Well, you remember for an ideal monatomic gas, the change in internal energy was 3/2 NK times the temperature change. But since there's no temperature change, there's no change in internal energy. And so at the end of the process, the internal energy is the same as it was at the start of the process. So that was A. Question B says, how much work does the gas do? We touched on this before, right? And so I can draw a PV diagram like this, and I can say here's P1 and V1, and here is P2 and V2, and it's going to kind of do this like that. These are points A and B. And so the path it takes is one of constant temperature. And so this is called an isothermal path, or just an isotherm, if you want to call it that. And again, this is equal to 3V1, right? It's final volume. And so if we want to say the work done by the gas is equal to the integral of P dV from V to 3V, right? That's what we said. I'll call this V initial and 3V initial, V final equals, or something like that. And so this is a complicated problem because no more do I have a constant volume, a constant pressure here, right? But what I know is that the temperature is constant. So if I take the ideal gas law and write PV equals nRT, this side is constant, so then P is equal to nRT over the volume. And so I can write the work by here as the integral from V initial to 3V initial of nRT over V dV. And since nR and T are all constants, I can say that's the integral from V initial to 3V initial of dV over V. Again, it's an isothermal process, so T is constant. This will be a standard technique for calculating the work done by a gas for an isothermal process. And so this is nRT times the evaluation from V initial to 3V initial of the integral of that, which is just log of V. And so the work by is equal to nRT times the log of 3V initial minus the log of V initial, which is nRT times the log, if you remember your log rules, 3V initial over V initial, which is equal to nR, let me write it back here, work by equals nRT times the log of 3. Hopefully I got all that on there. I think I did. Right? And so this is 1 mole times 8.314 joules per mole Kelvin times 300 Kelvin, for the whole process, times the log of 3. So what I get for that is the work by the gas is 2,740 joules. Again, the gas is expanding because it's moving from left to right on the PV diagram. And so the gas is doing positive work. I could say the work on is the negative of that if I wanted to. And so I'm going to come up here and answer the last question, question C. Is so what's the heat added in this process? Well, the change in internal energy is equal to Qn minus the work by. But we already know from part A that the change in internal energy is 0, and so that means that Qn is equal to the work by, which makes sense, right? If you want to keep a constant temperature, however much work you're doing, you have to replace that much heat so the gas doesn't cool down. And so this is just 2,740 joules. Isothermal processes have no change in internal energy.